next time. I'm also going to record this because there may be some people like UJ who may not be able to make it here. Okay, so as I had noted, I wanted to discuss this topic, which is going to concern the intersection of category theory and data analysis. And we will begin this discussion today with some reminders, but continue on to a discussion of particular application with formal concept lattices that I believe could be actually really very valuable in the nearer term for some data analysis concerns, particularly where we have dichotomous data that's where we have true or false, for example, true or false reports. Like, for example, whether someone with long COVID has a certain symptom. So everyone here, I think, will be familiar with pre-order categories, where we have as objects particular quantities. We have objects, and then we have morphisms. It's a thin category, and morphisms represent, in some sense, that one thing. So morphism from A to B indicates that A is less than or equal to B. Commonly we do apply these like with sets, right? We have, well, the set elements of the set being the objects, and one set, if the one element is less than or equal to another, we'll have, so if A is less than or equal to B, we'll have morphism from A to B. From a standpoint of enriched categories, which some of you may have seen, this is a category enriched, can be viewed as a category enriched in Boole. Okay. One thing I didn't emphasize in my latest treatment of it in class for the 898 is the fact that we will commonly have within a preorder, if we have a preorder where we have a product and coproduct for all of our elements, and we have what are called meets. What we have, therefore, what are called meets and joins. And I've put the notation for those here in a way that is fairly specialized to lattices. So meets are denoted in this sort of way. Joins are denoted in this way. But the very nature of the denotation here should suggest this is very much a product type construct, and this is very much a coproduct construct. And when we have a preorder, this meets and joins for all objects, and there may be one other requirement, something about a top and a bottom, then this is termed a lattice. And lattices have properties that we're going to be talking about today, but most importantly, we're going to be returning to this notion of a meet, which is really the product of any two objects, right? And the join, which is the coproduct. So I think you'll remember these for some of our examples, right? So if we have like 3 and 4, the product of them is, in this case, preorder, right? It's the closest sort of upstream one that has a morphism to both of them. So 3 and 4, well, 3 is 1 to 3 and 3 is 1 to 4, so it's 3 here. That's the product, right? And that's our meet. The joint 4 is our join, which is also the coproduct of these, and that's mathematically here it's given by max. Here the meet is going to be and the or it's the join is going to be given by or. When we have something like this, we'll have and so this is we have a arrow from object A to object B. If A evenly divides B, right? We will have the meet be the so-called product in this category, which here will be the greatest common divisor of these. So like 2 for 4 and 6, the greatest common divisor is 2. And the join will be the least common multiple, right? And here, does anyone remember what is the product here? What's the meet, in other words? What is it?
Intersection is meet.
Yeah, intersection is meet. And what is join?
Union.
Union. Yeah, exactly. Okay. Okay. So we're going to be dealing with these lattices where any two objects have a meet and have a join. They're pre-orders where we're going to have these this meet and join structure. And commonly, and I think this may be required, they have a top and a bottom element as well that is within it. Okay. So the type of data we're going to be talking about, though, will consist of relational data. Data that consists of relations between a very specific set of things. So there'll be objects and there'll be attributes, and there'll be a relation between from objects to attributes, okay, between objects and attributes. So objects here will be individual entities. These could be people, if we're dealing with like people with long COVID and we're considering what symptoms they have. People could be objects. It may be, we'll see one example from Christ where objects are platforms for social media platforms. We may have other cases where objects are species of shrew or what have you. And then there's attributes. These are characteristics of those entities, of those objects, right? So for long COVID, it might be the particular symptoms that they have. So a particular person is an object, and the attributes might be the symptoms they have. For shrews, it might be some aspect of their the fleas that live on them, to use an example from presented in talk on formal concept analysis, or it might be for species, or not just species, but sort of groupings of animals, genera, etc. These might be their characteristics, whether they have fur or whether they lay eggs, etc. We have a relation. It's a subset of the product of these two, right? So relation is a subset of the product, the particular subset of the product for which, G and M are related, right? So R is the subset of the pairs of an object and an attribute such that the object has that attribute. There's going to be some where the object doesn't have that attribute, and those won't be in R. So, in a context that Jeff might recognize from his days supervising retail, here you might have products like electronic products in stock here, say computer types, and each of them has a particular set of characteristics. For example, does it have it's a bit dated, but a CD drive, a number pad, HDMI support, bio ID for security support, right? These are the objects, the laptops these are the attributes. So for a given object, we have some set of attributes that apply to it. And this table describes a relation, right? The cells that are, each cell is at the, reflects a product between a particular object and particular attribute. And if that cell is filled in with an X, that indicates, somewhat confusingly, visually, that it does have that attribute. If it's empty, then it does not. So this set R, so this whole table is G cross M, and R is the subset of G cross M. G cross M is going to be a pair of an object and an attribute, and subset R of it will be the subset that have these X's. Those will be precisely the pairs of object and attribute for which we have an X. So we're only considering here binary attributes. Here we'll talk about capturing ordinal data a bit later. So there are these constructs for formal. So there's this area called formal concept analysis that's been explicated quite nicely by Will and others since the 1980s, Will and Will's group. One of the very nice features of it is you have a lot of structure that's been explicated. So one of the key points to structure are what are called derivations. And these derivations go between objects and attributes. So given a set of attributes, a set of objects, one relation goes one way from objects to attributes. So it will tell you some attributes for those objects. What attributes will it tell us? Well, if we have a set of objects, a prime we'll use to denote a set of attributes. What set of attributes is it? What's the set of attributes that are shared by all of these objects of A? In other words, that have to be there for each and every object of A. There's going to be some set of objects, some set of attributes that are shared by these objects in your set. So maybe your set A is the boundary, laptop, and the cheese book. If that's your set A prime would be CD and BioID, because those are the attributes shared between these the set A, all of these, each and every one of these objects in A. By contrast, if you had boundary, cheese book, and let's say the tin book, they're going to share a set of attributes. What are they going to be? Well, you'll notice before with boundary cheese book, we had these two sets of attributes. But if our A is instead these three, boundary, cheese book, and tin book, their set of attributes that are in common between all three are just this one CD, right? Because the tin book doesn't have a BioID. So you'll notice the more things we get in our object set, the fewer attributes have. And I need to acknowledge this wonderful video from Summon Product called Formal Concept Analysis that I encourage anyone to watch. And I'll draw some of my slides or some of the graphics on the slides from that, as well as from another talk by a researcher in this area. Okay, so this is one derivation, it's called. Given objects, we can get attributes. All the attributes shared by each and every one of those objects. Okay, for attributes, there's a derivation going from attributes to objects. So if we have a set of attributes, we're going to use G to denote objects, M to denote attributes. So here we're dealing with B subset of M. In other words, a subset of the attributes. B prime, given our attributes B prime is the set of objects that share all of those attributes. So the set of all the objects that have each and every one of those attributes. So for example, if our attributes were something like the HDMI and CD, well, we're looking for objects that have, we must have objects that have each and every one of those. Okay, well, one of those objects would be the cheese book. Another object would be the tin book, but nothing else has both of those attributes. So this, here we're going from attributes to objects that have all of those. So again, these derivations go from one to the other. So this one goes from objects to attributes and is for a given set of objects, it's all the attributes shared by those objects. Whereas this one goes from attributes to objects, and for a set of attributes, it's all the objects that share those attributes, that share all of those attributes. You notice the for all in each of them. Okay. Now, from these derivations, which are related to Galois connections and underlying adjunction in category theory, it's quite beautiful. The following are guaranteed. So if you take a given object, set of objects, and you ask for all the attributes shared by them, shared by each and every one of them, and then we ask for all the objects that share those, that has to be at least as big as your original set of objects. It might include others. Maybe your A didn't include some that have all of these. But all of those that had all the original objects, or sorry, all the original attributes, this is A prime is all the A prime, just one prime would be all the attributes shared by that set A of objects. And then one more prime will be taking those attributes and finding all objects with them. So your original A is guaranteed to be a subset of these. It's some of those that have all the objects. It may not be all. But more than that, if we have a set of objects, and we take its A prime, so we get the attributes shared by all those objects, each and every one of those objects has, shared by each and every one. That's equal, that's guaranteed to be equal. This set of attributes is guaranteed to be equal if we take that, we convert it back to objects, and then we convert it back, we use the derivation to go back to attributes. I mean, after all, a double prime is the set of all objects that have those attributes in A prime. And if we convert it back to school, what are the attributes shared by all of them? They're actually equal to the number to the attributes shared by the original set. They're the original ones shared by them. That may not be obvious, but if you want to think about it, I've tried to provide explanation in some of the words here. But I also hinted earlier at another important property. And this is a very pleasing property, but it's contravariant. Just like with other cases of contravariant, it probably merits pause for reflection. Okay, so here's the deal. Do you remember when I asked earlier? I asked, like, what attributes are shared by the boundary and cheese book? And we found that it was the CD, and we found that it was the bio ID. Do you remember that? Those are the set of all attributes shared by these two, right? That's so if A is these two, A prime is CD and bio ID because they're shared by these two. If we went to a third now we're looking for a more constrained set, right? We're looking for the set of all attributes shared by all three. And in fact, in this case, with the tin book, we didn't have the bio ID anymore. So that constrained, that limited our set, right? Of attributes that are shared by all three. You might think going from smaller number of objects to a larger will expand our set of attributes. No. because this is a very specific criteria, they have to be, we're looking for all the attributes shared by each and every one of those objects. If we have more objects, it gets more constrained because we're going to knock out anything that isn't shared by that third one, right? And so as we add a third one in, it's getting more constrained. So look, here's the thing. If a set of objects, A, is a subset of another one, B, if B has more things, like it's 3 instead of the 2, then the set of attributes shared by those 3 are going to be a subset of those shared by those 2, right? It can be no larger than it. It can only grow more constrained. The more objects we have, the more constrained the set of attributes are that are shared by all of those objects. So if we add a third, a fourth, and fifth, the set of all, as B becomes even bigger and bigger than A, the set of all attributes shared by like all 10 of those, all 20 of those objects, is going to be a smaller and smaller subset of the set shared by our original set, right? Kind of stands to reason. But you notice it's contrarian. A is less than is a subset of B here, but B prime is a subset of A, right? The order is reversed, right? A and then B here, a subset of B here, B prime subset of A. Okay. Now there's a notion of certain pairs of object sets and attribute sets that are special, that are consistent, that are kind of go and that are distinguished. They're called a concept, and they have very specific properties to make them a concept. They have very specific characteristics, we'll call it extension and intension. Okay, look, if we have a set of objects, we consider all the attributes shared by each and every one of those, and then we convert back to the set of all objects that have that has to be equal to A. So A is like this maximal set of objects that have these characteristics A prime. And if we have a set of attributes, I should have said the concept is a pairing of an object set and an attribute set. And so I just emphasized the property for for this to be a concept within our lattice, within our ideas. A concept that's distinguished the fact that the object set is kind of the maximum one that has those shared features. And the attribute set is also very particular. If we take that attribute set, we consider all objects that share those attributes. And then we ask, what are the attributes shared by all those objects? It has to be the same. So in some sense, it has the sort of full set of attributes shared by these, all of them, all the attributes and none of them shared by these, by these objects paired with it. And those attributes have to be the attributes of these objects. So we call, if A comma X is a concept, again, A is objects, X is attributes, right? We're dealing with this relation, right? Objects, attributes here. If we have this concept set and its corresponding attribute set that have these nice properties, sort of natural property, they have a natural extension, natural intension, then we call the object set the extent of the concept. Those are sort of all the objects that have it. And we call the attributes the intent of the concept. Those are all the attributes they share. And it should be noted that if you have some object set within your set of objects, you can automatically get a concept by taking A triple prime. converting to a set of attributes shared by all of them, converting back to all objects that share those attributes, converting it back to the attributes shared by all of those, and then the attributes shared by its original set. That is going to be one of these concepts. It's kind of stable, sort of like natural maximal, sort of natural pairing of these. Now, you may be wondering, like, I started talking about lattices, like, where do those come in here? Well, look, we're going to have an ordering of concepts. This should remind you of like a pre-order categorically, right? If we have two concepts, special things, two concepts here, pairings of set of objects, set of attributes. If we'll call AX less than or equal to BY in this kind of pre-order. So we'll have these, should have said the objects will be these concepts. And if we have one object, AX, another object, BY, there'll be a morphism saying less than AX is less than or equal to BY. If A consists of a subset of B's objects or something no bigger, subset of it. And therefore, Y, remember the contravariance, remember this contravariance, Y's attributes, because B could be a bigger thing, Y's attributes are going to be a subset of X's. They could be as big as X's, but they can't be any bigger because they're more constrained. They have bigger number of objects they have to account for. Okay, so look, if we have a lot more, and you'll notice we started to deal with ordinals here. We have all these objects and we have these attributes. And we sort of took these ones which are ordinal and turned them into sort of dichotomous ones by having these less than or equal to, can I get this for less than or equal to 1,500 euros or 2,000? Again, I want to give, my deep appreciation and credit to this video, which is just outstanding on formal concept analysis, and I'd recommend from which I drew that slide. Okay, so we have these notions of this. We can arrange this into our pre-order, right? We have this notion of pre-order here, giving you, how to arrange the morphisms and what the morphisms are in the pre-orders. The objects are these concepts, right? Morphisms are these less than or equal to relations between concepts as defined here. So we can arrange these, and again, this is from that same outstanding video from Summit Product. So here we've taken all these and we have labeled the extent, the object set for each concept, and we've also labeled the intent. Remember, the intent is the attribute set associated with those concepts, right? So this one has just a boundary associated with it, and it has all these sort of characteristics here associated with it. In this excellent video, the author, abbreviated it to I think the smaller set we were dealing with before, just to make it more manageable. And you'll notice that there's these orderings on this, in this pre-order, right? But these orderings are not willy-nilly. The orderings have a logic to them that's quite powerful. For example, this set of attributes here is no smaller than this set. You'll notice as you go down here, it can only become larger, right? And this gives a real structure to this, which is rather pleasing. I will note that this should have had a BO next to this. So there should have been boundary book, because the boundary book has CD, HDMI, and BioID, right? Boundary book is CD, H. Oh, it should have a HDMI. Okay, this should be. It's probably a different one. This is probably like CH, the cheese book. This is probably the cheese book. Yeah, this should be cheese book. I think that's right. Yeah, yeah. But you notice if you take that into account, the object sets, as you relax the attributes they have to have, the object sets can only grow, right? All those to satisfy this more constrained thing, and more attributes are a subset of the objects that satisfy this less constrained set, right? Further you go up, the more objects you have. Further you go up, the less restriction on attributes, the fewer attributes by which you're you're requiring them to have. But the more objects, therefore, that satisfy those relaxed constraints. Now, so this encodes this sort of or the subset of this table, right? Here. This is from Robert Grice, again, outstanding lecture. I can move this up here, which again I'd recommend to anyone. It's actually part 3 of a lecture on sheaves. But okay, somehow this is I just want to get that out of the way. So here's our Galois lattice, and this relates to work of one of his students, Hans Rice. I did deep learning on these lattices, and here, look, we have objects being social media services. We have attributes being the characteristics of them, and we are recognizing here for each service. This is our objects, right? So you may remember the objects can only grow as you go up here. And YouTube here has, as an object, we could talk about its upset here as including all of its characteristics as labeled here. We label a characteristic here, and I'd have to get this right, as I think this characteristic labels everything lying under it. So all of these, I get that right. So yes, the downside. So if we're interested in ones that allow for maybe it's downloads, perhaps it is. No, down voting content. Well, down voting content is something that's supported, for example, by Reddit. It's supported by YouTube here, but it's not supported by certain of the services like Instagram or Twitter. Therefore, it's not beneath it in the lattice. So if we want to understand the attributes that apply to a given object, we look at its upset. Notice here we actually labeled it explicitly here. We didn't have to go and appeal to the upset, but if you wanted here, you could have said, we're going to look to the upset and just labeled it with the last time going down that it's seen, I think it is. But here we could look at the upset to find the characteristic for a given object. And we look at the downset from a characteristic, like whether you can upvote, to find all the objects that allow upvoting, which here will be like Reddit and YouTube and Instagram and Twitter, etc., because those are ultimately reachable down here in the lattice from there. This is really just two different ways of presenting the information. This one has a more sparse characterization visually. To find out, you have to reason out upsets and downsets visually, but it's really the same information as contained here. And you have the same basic characteristics that the further you go up, the fewer and fewer objects remain, or excuse me, the less and less constrained the attributes that have to be present. Therefore, the more and more objects here, platforms that abide by it. The further you go down, the more and more constrained the set of characteristics that you require, the attributes that are required for those objects. This is an example that I found from this outstanding talk by Bernhard Ganter, who's a leading researcher in this area from Willa's group, where Willa worked on it as a mathematician from the 1980s. So here, look, objects are people, and attributes are clinical characteristics as scored as reported by the person. And again, it's a relation, right? You have true or false for every pair of person and this. And this is actually like their perceptions of their ideal, etc. And this is for patients suffering from anorexia. And we can go and characterize a given relation in this sort of lattice type way, in a way that gives insight into the structure. And so, for example, here, the father and the sister are characterized by attentiveness, is what this person infers, or she believes her sister and her father are attentive, but that her mother here is not attentive because the mother doesn't lie underneath the attentive. It's not downstream with the, or it's not in the lattice beneath the attentive node. There's no join of the mother with other things that will lead to attentive. So here you've seen some about like the basic rules and basic structure and how we can diagrammatically indicate this data. But there's a key portion that I haven't told you about yet, and that has to do with what are called implications. Okay, has to do with the logical structure and explicating that logical structure in terms of implications. Okay, look, if for attribute set X in Y, these are attribute sets. If X prime is less than Y prime, in other words, if all objects with attributes X, remember X prime is set of all objects that have each and every one of those attributes. If that's a subset of set of all objects that have attributes Y, right? Then it means all objects with all attributes, and thus it follows that all objects with all attributes X also have attributes Y. So if it's the case, in that case, we say X implies Y. Okay, so for attribute sets here, if it's the case that all objects with attributes X are a subset of all objects with attributes Y, so every object with attributes Y has attributes X, then we say X implies Y. Okay, so we know Y is true if we know X is true for attributes. We know Y is true for attributes if we know X is true for attributes. And these implications can be generated, can come out of the structures here. We can deduce these from these structures. So look, if y is less than or equal to x, then x equals y. So look, if the set of objects with full attribute set x is directly, and remember these are concepts, and if it's directly a subset of possibly less restrictive y, then x equals y. But more than that, if we have a set of attributes and we consider all objects that have them, and then take all the attributes that those share, that's the x double prime. So we go from attributes x to all the objects that share them, back to all the attributes that those share. We have at least the attributes from x. Remember that? So x here implies y prime. If so we know that if x holds, then we know that this concept holds. That's why these set of attributes hold. We know these sets of attributes hold. So if this set attributes x holds, then x double prime holds. More than that, I should remind you of categorical structure here. It's just yearning to be identified. We have composition. If x implies y and y implies z, then x implies z. Okay. So time is running on, and I really need to get home for this important physician phone call. But I want to talk about this. So having implications, there's some really interesting things that can be done. So one thing you can do is look for minimal attribution. Like you want to have a desired you want a minimal set of attributes such that the attribute z holds. So you want z to hold within your set of data. So maybe you want the fact that you have an HDMI port or something like that, or that it's available for less than 1,500 euros, something like that, less than or equal to 1,500 euros. And you're going to want the minimal set of attributes such that Z in fact holds. And that if you remove any of those attributes, Z will no longer hold. So it's here remember, the more attributes we have, the fewer the objects. The more attributes you have, the fewer the objects that have them. If we knock out attributes, we can have more attributes that obey them, and those attributes may have a greater diversity. They may not have Z anymore, right? So here we're trying to find like a minimum set of attributes that guarantee us Z. Here we are seeking to find a minimum set of attributes, for example, which will provide some attribute that we judge good, and this algorithm can help you reason about it. But more generally, and I think for my interest, it can help reveal the structure of data that is dichotomous. We in our health science application work, we have a lot of work going on where we have numeric data. And when it comes to vectors, right? And vectors of real numbers. But when it comes to ordinal data, or particularly when it comes to dichotomous data like this, our tools are actually quite a bit more limited for drawing insights from this, for realizing the structural implications. And between the idea of implications and the logical structure of it, the idea of finding minimal attribution sets, or even diagramming out this structure, and and characterizing, which attributes apply in more sort of strategic positions and which are further down, which include all others. There may be some attributes that others follow directly from, right, that are implied. I think we can work to actually explicate the structure of our data when it comes to dichotomous responses here in some really interesting ways. And we may discover some hidden structure there that we would not have found by running a regression or doing machine learning algorithm on it, just treating these with one or zero variables or what have you. I think we might be able to use this for some important insights. And I'm not even talking yet here about reasoning about morphisms, which are structure preserving mappings, that is monotone maps from one lattice to another, which has huge potential, relating how one person responds in terms of their pain levels or in terms of their functional limitations to how another does, reflecting the fact that they may use somewhat different standards for describing it. But if they're saying one thing is worse than another, that often that's going to be preserved for the other person. Anyway, I'm going to stop here. I got to get home, and I want you to chew on this and think about it. And I'd encourage you to refer to these outstanding videos, and the great thought behind them. I would note there's a book by Bernhard Ganter and Rudolf Villa on formal concept analysis. There's also a great video of Bernhard Ganter in Moscow, and this outstanding introduction from which I've drawn so many of these slides, in addition to these slides from Bernhard Ganter. Okay, that's all I have time for now. Hope that gives you some food for thought, and I look forward to discussing separately. Take care there, and I'll be taking other meetings today from home. Take care.